Imagine a coin spinning on a table. As long as it remains in motion, you cannot say whether it is heads or tails. It exists in a blur of possibilities, unresolved, right up until the moment it is forced to stop. The devices we rely on today operate on the opposite of that blur. Our phones, laptops, and servers require absolute certainty, processing information strictly in distinct ones and zeros. Early classical computers relied on physical, mechanical switches to flip between these binary states. To calculate an output, these machines read every line of code one step at a time. This sequential logic built the modern world, but it also creates a strict ceiling. If a problem has too many variables to check one by one, a classical computer simply runs out of time. Nature doesn't use a binary alphabet. In the natural world, biological and chemical systems exist in an intertwined blur of simultaneous possibilities. When we try to model a weather system or a new drug interaction, we are forcing nature's fluid motion through a narrow, linear funnel. A traditional processor must calculate every individual interaction one after another. This creates an inherent translation problem. We struggle to solve our most complex mysteries because our machines do not speak the universe's native language. The solution is the qubit, the fundamental building block of a different type of hardware. Returning to the coin metaphor, a qubit behaves like the spinning coin rather than the landed one. Through a property called superposition, it avoids locking into a 0 or a 1, instead holding a mix of both states at the same time. Maintaining this delicate state requires isolation from the classical world. Qubits are housed inside these tiered golden structures, dilution refrigerators that use liquid helium to reach temperatures colder than deep space. By sustaining this unresolved state, every qubit we add to the system doubles its computational capacity. With just 300 of these units, a machine could theoretically represent more states than there are atoms in the observable universe. To see the difference, imagine a maze. A classical computer finds the exit through sequential testing. It traces one path, hits a dead end, turns back, and tries the next. A quantum computer behaves like a fluid, explores all possible paths simultaneously, and floods the entire maze to find the exit in a single operation. This is possible because of entanglement, a link where qubits are so intrinsically correlated that a shift in one instantly influences the others, regardless of the physical distance between them. As these entangled qubits work in unison, they use quantum interference to guide the calculation. Like waves in a pond, they amplify the correct solution while canceling out the incorrect paths. This does more than increase calculation speed. It changes the physical approach to problem solving, allowing us to find specific solutions within data sets that are too large for traditional logic to navigate. These systems will likely remain inside specialized labs and commercial computing centers. They are designed to act as high-power lenses for problems that are currently too complex to see clearly. In pharmaceutical research, they can accurately model protein folding and simulate how drug candidates interact with enzymes like cytochrome P450. This allows researchers to identify promising treatments without the trial and error of classical simulations. In material science, these simulations can map the molecular interactions required to design more efficient solar cells and high-capacity battery technologies for the energy grid. By calculating the behavior of matter at its most fundamental scale, we are gaining the tools to optimize the physical systems our society depends on. However, this ability to navigate complexity poses a risk to our digital security. Shor's algorithm has already demonstrated that a sufficiently powerful quantum computer could factor the large numbers that our current encryption relies on. Because quantum systems can find these mathematical factors exponentially faster than classical ones, they could render modern privacy protocols obsolete. This has triggered a race to develop quantum-safe cryptography before these machines fully mature. We are learning the universe's hidden language to solve our most difficult material challenges, but doing so forces us to completely rethink how we secure our information. Time for today's curious question. If you had access to a machine that could simulate any molecular interaction, what scientific mystery would you want to solve first? Let us know in the comments, and be sure to check out the other videos on your screen to keep learning.